That's total dedication for sure. All right. Yeah. Yeah. Thank you everyone for joining us today. My name is Rafael Moreira. I'm president and founder of Ready Institute. So this is a SUMA series organized together with PRI, where we have the principle for this connection between both Institute Ready and PRI is Melody and Chitta. Today she's going to be just in the background here, listen to and listening and reading our discussions here. So that's very nice to see you all. Yeah, I'm at the moment, I'm just trying to multitask here. At the moment, I'm here in Germany, in Bremen, and I'm a researcher and full professor here at the University Bremen, in chemistry department. And today we're gonna be hearing about, or at least learning and discussing, hopefully, about lots of pigments and color and lots of chemistry around that. So we have our presenter today is Elisabeth. Say hello there.
Hello.
So yeah, Elisabeth is a recipient of Rhodes Scholarship in Research and Travel in 2020 to study pigments in Cyprus. Elisabeth was also the founding director of a studio lab at the School of Arts Institute of Chicago, where she educated SIIC students on how to make and use traditional and modern painting with drawing materials between 2016 and 2022. So in this role, she developed educational resources, collection including a library, material archive of historic paintings and materials, and a virtual database of instructional videos, which is amazing. I would love to check them out for sure. And use them on one of my lectures here. And she has been a member of the ASTM Artist Materials Subcommittee, as well as the Gold Artist Educator since 2017. And she's received a Rhodes Scholarship for has exhibited widely in group exhibitions throughout Chicago and the Midwest. Yeah, so without further ado, Elisabeth, please, uh, the floor is yours. Thank you very much for accepting our invitation to share your knowledge with us. And before we begin there, I would like to ask you all to, if you have any questions or comments, just put in the chat. We can have like a Q&A, hopefully, perhaps in between the like changing topics or at the end of the present Elizabeth presentations. Okay, thank you very much.
Thank you. Hello, everybody. I just one clarification. I have a Fulbright award, not a Rhodes Scholarship. So that's why I'm here in Cyprus, which is where I'm zooming from today. Um, so I'm going to go ahead and share my screen for everybody to see. Um, and I'm just going to jump in. I will not be able to monitor the chat terribly closely while I'm in the
Don't
midst of
worry,
things.
don't worry.
Okay.
Yeah, I will do
Okay.
that.
Thank you. Yeah, I like know my multitasking limits and I can't I can't do both. So without further ado, we are going to jump in. Today's presentation is called Binders Hold Pigments Together. Um, binders are the messengers of and the carriers for pigments in paint. They are the lens through which we see and experience pigments in art. And they're often the unsung heroes. Like we learned about a lot about pigments. They're very pretty and bright and cool, but binders are really the things that are imparting some of these unique qualities to paint. And so I think they deserve some extra special attention. Binders are a tool in this sort of kind of magic that artists can use to wheeled pigments to use them. If pigment and color is the melody and the musical notes, the binders are the dynamics and the rhythm and the tempo of the music. They're really the things that's giving the shape and the character to paint. I do want to say I've had the opportunity to work with and learn from conservators, paint manufacturers, scientists, archaeologists, historians, all sorts of different people. And I'm really speaking to you today as an artist, which I think is an important distinction to make. So, a lot of the recipes for how to make things are not things I'm really going to cover today. I'm more going to talk to you about the experience of working with these things and help you to kind of understand it in a more hands-on kind of way that hopefully makes you feel like you've gotten your hands dirty a little bit. So this presentation is going to be kind of like 3 chunks. The first chunk is we're just going to be talking pigments, binders, paint, what's going on there. The second chunk, we're really talking about pigment binder relationships and the factors that kind of come into play there. And then in the third section, we're going to go through some like nitty gritty different paint mediums and understand what some of those things are. So before we do that, what is a pigment exactly? Probably a good place to start. A pigment is a type of colorant. The colorant just in general, right, is a substance that colors something. A dye is a soluble colorant, usually an organic material that chemically bonds to the substrate to which it is being applied. And so the important things to remember here are soluble. The dye itself, the material of it dissolves into the dye solution. Usually there's a metallic salt or something like that involved as a mordant, whereas a pigment is an insoluble colorant. So it's really holding on to its discrete physical form in the paint film, which is a very important distinction. It can be organic, it can be inorganic, and it's not attached to the substrate through a chemical bond, but more so mechanical, through mechanical adhesion, dispersive adhesion, and other types of adhesion like that, less so chemical. So the question here is, how do we take pigments in their powdered form and get them into paint? That is why we're here. So what is a binder? Right here on this slide, we've got just some different, just like a mood board for what binders are. We've got acrylic, we have egg yolks, we have linseed oil. On the right is the gum arabic, which is a binder for watercolor, both in its physical form and also in its liquid form. So a binder is the component in paint that adheres pigment particles to each other and to the substrate and defines the unique qualities of different mediums. So the binder is really what's giving the character and the context to the pigments that we're using in paint. Some different types, this orange section right here, we've got gums, proteins, vegetable oils, natural or synthetic resins, waxes, etc. These other, the yellow and the green, they're more like related sub-definitions of a binder. That's not, a definition of a binder, but related words are a medium. So that kind of has 2 definitions in paint. A medium is the substance an artist uses to create their work. So it's like, oh, what medium do you work in? I paint with oil. That would be like your medium. Or it can also be a material added to alter the binder behavior. So maybe I paint with oil and I add cold wax medium to change the characteristics of the paint. And then also another term that kind of gets wrapped into this little stew over here is vehicle. And the vehicle refers to all components in paint except for the pigments. So that would include the binder, that would include any mediums that you're adding into it, that would include a solvent if you're using solvent, etc. So really, binder sticks pigment particles to each other and to the substrate and is the lens through which we experience pigments. Putting it all together, we've got pigments are small particles that remain insoluble in liquid paint. Binders or vehicles, the same kind of pigments for the most part. There are quite a lot of exceptions actually, but for the most part, the pigments are going to be consistent whether you're painting in oil or watercolor or acrylic. There are certain pigments that have alkalinity, sensitivities, and other issues like that that are not compatible with different mediums. But for the most part, pigment stays the same. The binder, the adhesive is changing. And then rather than dissolving pigment particles and binder molecules create a heterogeneous suspension. So what does that look like? Here, these images are from the Gamblin oil paint website. And it's just like a really good visual to imagine these discrete pigment particles that retain their form while they're in a paint film. So on the left, it's showing the drying of oil colors. The top diagram is showing the big blue blobs are the pigment particles, and then the little squiggles in between are the molecules of the binder. So in the case of oil paint, it starts as like monomers of linseed oil that as it dries, the oxygen comes into the paint film and the monomers link together and create longer little strings of the oil, and they kind of knit together and keep the pigment particles in place. And on the right side, we have the drying of acrylic colors, which is like a similar process overall. You've got the pigment particles, you have the binder in between and around the pigment particles. But in the case of acrylic and all water-based paints, you have things evaporating out of the paint film in order for it to dry. So in some cases, it may just be water. In the case of acrylics, you've also have ammonia, propylene glycol, and other sorts of chemicals like that. And because acrylics dry by evaporation, the paint film actually loses a lot of volume as it dries, which is kind of interesting. Oil pretty much keeps its physical volume and actually gets heavier for the time that it's like sucking in the oxygen, which is kind of interesting. Okay, so on a large sort of industrial scale, the paint that we buy at the store, what they do is they have these like massive amounts of pigment in these giant boxes that I can't even imagine having that much pigment in one place. And they have, big scoops. They put it into a large sort of standing mixer in order to just kind of roughly incorporate the pigment with the binder, whatever that binder may be. These images are from M-Gram. It's like I screenshotted out of a video that they had about making oil paint. So pigment binder goes into this giant standing mixer and gets mixed together. From there, the paint is kind of scooped out and placed into this machine, this large standing machine called a 3-roll mill that has these rollers on it that are made of carbon steel. You can change them out for different materials if interested, like granite or something like that. You can change the distance between the rollers. And what happens is they're basically rolling in different directions and at different speeds, and they're squeezing the paint in between the rolls as it's going. And so what's happening there is this kind of coarse mixture that just got blended together in the standing mixer. You still have all these like clumps of pigment particles. And by putting it through the 3-roll mill, you are breaking down the clumps of pigment particles and having kind of each little particle nicely wrapped in binder molecules, as we kind of saw in the diagram a few slides ago. So if you would like to make paint and you don't have a 3-roll mill at your house, like I also don't, I'd like to show you just on a more understandable scale what that looks like. And I'm sure many of you are very familiar with this process. Here I'm using a green earth pigment. I am making oil paint in this video, but this process kind of looks the same no matter what binder you're using. We've got the pigment, I'm using cold pressed linseed oil. I've got a little pipette, which is helpful, but super not necessary. Palette knives, and then this is called a muller. It's made of glass. There are also different materials of the mullers. I'm using a glass muller on a glass palette. Both are sanded, like have been abrased with silicon carbide, which is basically like sandpaper stuff. And so you kind of grind the plate to prepare it so it has grooves to it. I have my pile of pigment. I'm adding the oil in like mashed potato and gravy style. And the first step is to really incorporate that. This cut in the video, I kind of show you the whole bit of time that it takes. It's not like jumping forward or speeding up in this moment, just so you can really get a sense of, okay, how long does it take to do this by hand? It takes a while, guys. It can be a laborious process. Very meditative process though as well. And you you know, just by feeling it and moving with the materials, get such a sharper understanding of what it is that you're dealing with. So don't be deterred by the labor for sure. But so what I'm really trying to do is I'm just trying to do the thing that the mixer does, which is just roughly incorporate the pigment with the with the binder. And again, I'm using linseed oil. And at this point, you kind of want it to be, you want to make your paint into kind of a stiff paste because when you actually do use the muller, which you'll see later, it just really spreads everything out and loosens it up. Right now, it feels kind of chunky, as you can see. But yeah, so that right there is about real time how long it took me to do that. But now it's going to jump around and it's going to be faster. So you can kind of just get the gist of the overall process. But adding more oil. And the other thing that's important about this video and also just this whole presentation is like every artist does things in such a different way. So for me, I kind of like working section by section, making sure I have that it feels right, that I have the right kind of amounts of things mixed together. I see artists who will just kind of like pour it all together and work with it in a mass. Same thing when you see me moving the muller later. I kind of work in like little sections, section by section, and then you have other artists who will just like use the whole palette. Wow, I got so fast at this. um, so yeah, here just incorporating it all together. One thing you can really, really see with this pigment is the drastic color change from when it's in its dry form to when it's being mixed with the binder. It's quite shocking, really. So with this big, chunky, sort of like matte, pasty looking stuff, I mean, anybody who squeezed out fresh oil paint from the tube, it's like glossy and sexy. Like this is not it, right? So now it's time to use the muller. And again, the palette, both the palette and the muller are kind of sanded and abrased on either side. And what that means is there's little grooves in the glass that are grabbing on to the chunks of the pigment particles that have like formed these agglomerates. So all the pigment particles are stuck together, which is why it kind of looks matte and chunky like that, because there's on the surface, there's all these like little exposed pigment particles. So what I'm doing by mulling it is I'm like using shear force to kind of pull these agglomerates of pigments apart, like tear them apart. I'm not grinding the pigment, I'm just tearing apart these clusters and agglomerates of pigment that are making the paint look kind of matte. And you can see as I'm grinding it, like it's getting nice and transparent. When I start pulling the paint off the muller, you're really going to see how much more glossy and lovely it looks than the kind of, yeah, matte, crusty looking stuff on the left side of my palette right now. And again, I'm kind of doing these swirling motions. You're not, one kind of misconception is you're not really pushing down on it. It's like you have the material that's in between the muller and the palette, the paint, and it's kind of suctioning the muller onto the surface. You aren't really pushing down, you're sliding across. I kind of do these little twisty things to use the edges of the muller to pull the paint back in the middle. This is just how I do it. There are a billion ways to do it. And yeah, I don't know. I think the more you kind of get your hands dirty and move material around, you'll kind of feel what makes sense to you. But yeah, you can really see the glossiness and the translucency that I'm starting to find in this paint. So here we are. Here it is. That's the pigment. That's the oil paint, pigment with oil paint. Okay. Yeah, goes from opaque to translucent because you're breaking the pigment particles into kind of leaving them by themselves within the binder, and matte to shiny. And yeah, once again, this is oil paint, but the same basic process applies to all sorts of paint. So that's kind of the end of like the basics paint pigment chapter. Now we're going to go into factors that affect the pigment binder relationship. Binders, yeah, the process is the same for making the paints, but the actual experience, like what it feels like and how it moves, is very different depending on what kind of paint you're trying to make, depending on what kind of pigment you're trying to use. And so this is just a list of some of the factors. There are probably way, way, way more. And then we're going to go into a few of these different factors with some slightly more in-depth examples. But some of the factors that affect pigment binder relationship are pigment particle shape and size, chemical composition, the viscosity of the binder, density of the pigment, surface tension and polarity, binder rheology, refractive index, and dispersion. So both behaviors, I'm talking like physical behaviors, like how do they move, as well as optical behaviors, like how do they look. And so on that note, we're going to start by talking about refractive index, which is like a, a big secret in paint. Like it's so important. And I think it's a concept that people don't fully understand, right? Whether a paint is transparent or opaque is like really critical information. It's going to change how you use it altogether, right? And the refractive index is really the factor that's affecting that. So refractive index is a number, and the number means light moves X times slower through this material than it moves through a vacuum. So when we're looking at this little pencil in the cup, which I know everybody has seen in school at one time or another, whether or not you remember what it is and why. The reason why it looks like the pencil's broken in half is because light moves 1.0003 times slower through air than it moves through a vacuum. And through water, it's 1.333 times slower. Light moves 1.333 times slower through water than it moves through a vacuum. So the light is passing through the water slower than it's passing through the air. So we're basically like seeing the pencil faster, I guess, through the air than we are through the water. And those same basic principles apply to pigments and they apply to binders. So when you're mixing pigments with binders, you have the refractive index of these two different materials that when you mix them together becomes like a relationship of what is the difference between those two refractive indices, which is the plural word of index. I remember being surprised to learn that. But so to help us like break this down a bit, we're going to take linseed oil. The refractive index of linseed oil is 1.48. And yeah, don't get freaked out by the numbers. We're just going to think about them. We're not going to do any serious math. 1.48. Thinking about some white pigments. Titanium white pigment, PW6, the refractive index is 2.72, which is like what, 1.2 plus more than the refractive index of linseed oil. Zinc white is around 2, it's 2.02. Lead white, there can be a range, but from like 1.9 to 2. And then chalk, calcium carbonate, something like that is going to be like 1.51 to 1.65. Now, when you mix chalk with linseed oil, that refractive index of 1.51 with the 1.48 refractive index of linseed oil, the difference is very small. It's like 0.03. So they almost have the material, light moves almost the same speed through linseed oil and chalk, basically. And so what that means is that when you mix chalk and oil paint in linseed oil, it's going to appear extremely transparent, which is why we can use chalk mixed with linseed oil as a medium in oil paint to change the behaviors and the characteristics of the oil paint without really affecting the color. So that's very interesting. Whereas titanium white with the refractive index of 2.72, that's a very big difference in this like world of small numbers that we're talking about. It has more than a whole digit of difference there. So titanium white shows up extremely opaque in oil paint, which is a big factor there. So the basic thing to take away from this, forget all of the numbers. It's how similar is the refractive index of two different materials. Like when you're mixing the binder with the pigment, the different refractive indices sort of form their own equation. And the closer they are, the more transparent, the farther they are, the more opaque is the most important takeaways there. So now talking about particle shape, I'm sure there's like a lot more nuance to this. But some of the main particle shapes, we've got spherical. So just, rounded, consistently shaped particles. This is pretty standard particle shape of a lot of synthetic pigments, more standard in their sort of particle shape. Nodular is rounded, but more irregular and have crystal-like formation. So here we're getting into some more exciting shapes, one could say. Acicular particle shape is like a long, thin, needle-like particles. And then lamellar, I don't know if that's how you say it, but these are like plates. These are large plates. And so the shape of the particles is going to really affect the way light passes through it. It's going to really affect the way the paint moves. It's going to really affect the way it feels. And so here on the left, I have a micrograph of perlite that I took. And perlite is this really interesting volcanic glass, basically, that heats up and pops like popcorn and forms these little glass bubbles. And so that's like literally what we're looking at, these like little volcanic glass bubbles. And when you work with it as a material, you can almost hear it like the hollowness and the sort of like jingle of, I don't know, it has a kind of interesting sound to it. And it's extremely lightweight, but does have coarseness. And so it's like you see this image, and I think about the way I know this material feels and moves, and it's like, oh, of course, there's so much that we can understand through that. So snack break. On the left, we have a jar of bubble gum. And on the right, we have a bowl of pretzel sticks, which I'm sure everybody, if you can't picture the way perlite feels under a pellet knife, you can definitely picture the way it's going to feel to reach into a bowl of pretzels or into a, jar of bubble gum or something like this. We can look at it. We can see the way the bubble gum forms like a solid wall. We can just see that one first layer that's touching the glass. We can't see through it at all. Whereas the pretzels, we're seeing all of these layers underneath it, the layers of different pretzels. You can imagine that if you reach into the bowl of pretzels, they're all kind of like knit together and connected, and they're gonna move. You can't just take out one pretzel, it's gonna move the other pretzels around it. Whereas you could very easily take out, one piece of bubble gum. And this is we're still talking about pigment particles, if you didn't know. But so on the left, we've got spherical particles, very regular. They just stack together. You can kind of start to imagine how light is going to pass through a paint film when pigment particles have this shape versus how light might pass through a paint film when they have acicular particle shapes or other of the particle shapes that have a lot more irregularities to it. And the last thing I want to say about particle shape is think about like taking a piece of just sort of like bad quality computer paper and you rip it in half and it just rips in half, no problem. And it's made from paper pulp, which is these like small little fibers. And then think about taking a piece of like nice watercolor paper that has these long strands of cotton fiber and it almost like doesn't want to rip and then eventually kind of like feathers apart like this. Um, that same kind of logic is happening inside of the paint film. When you've got pigments that have irregular particle shapes, it is knitting the film together in like a very mechanical uh, way. Whereas if they're all, the bubble gum is going to rip like a piece of computer paper. The pretzels would rip like a piece of really nice cotton fiber watercolor paper. So hopefully these very disparate images helps to kind of contextualize that in a paint sense. Okay, now we're going to talk about density. Here we have 2 quart-sized plastic containers of yellow pigment filled to about the same height. So about the same volume of pigment is what we're looking at here. Number 1 on the left, number 2 on the right. Pop these babies on the scales. Number 1 weighs 7 ounces, which is 198 grams, which is almost nothing because that's a whole entire quart of pigment, right? And number 2, okay, and number 1 is Hansa yellow. It says it on the screen. Number 2 weighs 1 pound, 13 ounces, which is 822 grams. So it's the same volume of pigment. It's it's more than 4 times the weight, right? And so what we're looking at is we're looking at a pigment that is way, 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 way denser than the other pigment. And so that's not like, okay, we can see the number on the scale, cool. But that is going to affect the way it moves, the way it feels, and the way we're able to use it. Like even if you look at this first image again, the number one is the super lightweight one. You can see how the pigment is like clinging to the plastic of the container. And when you open it, it just kind of like poofs out. Whereas the cadmium on the right, it's heavy. It's just sitting there. It's not going to be bothered by just like a little draft of air, the opening of a lid or something like this. So these are important things, observations to make as you're working with pigments. It's like every little thing is going to figure in somehow to the equation. And the more we pay attention to what those details are, the more we can kind of anticipate, okay, what's what's going on here? When I start to mix this with other things, what's going to happen? And that's exactly what we're going to look at right now. So on this little palette, I have a synthetic iron oxide, I have a synthetic ultramarine blue, and I have a Hansa yellow, that same Hansa yellow. That's just like distilled water. So right now I'm just going to like wet the pigments, mix them with the knife. And this is really the first step to making water-based paints. You first want to wet it. So as I'm wetting the iron oxide, synthetic iron oxide PR101, it just like slurps it up. It's super happy. The palette scooted. It kind of, is compacting and sliding like the mud under your boot or something. You can see that there's a density to it as it's wetting. It's just kind of collapsing on itself. And that was super easy. And now this is the ultramarine, just like dropping some water in. I always recommend go really slow as you're adding any sort of liquid into the pigment because sometimes weird stuff happens. And the smaller amounts you are doing at once, the more you're going to be able to kind of manage it. So here, this ultramarine, it's automatically, like right from the get-go, it's feeling a lot looser, greasier. It kind of slides a bit more. It has a more sort of like rounded quality to it. Okay. So a little more rounded. And then this is that Hansa yellow I was telling you about, which weighs nothing. And it is also an organic synthetic pigment. The other two were inorganic pigments. And it's like, I have the water trying to mix it, and it's just not gonna go. So what we're looking at here is an issue with, well, not an issue if you're not trying to mix them, but the water is polar, the pigment is nonpolar and hydrophobic, and they just have no desire to become a mixture of any type. And so when you have two things that are repelling against each other, like literally the water right now is just like underneath the pigment and the pigment is floating on top. There is no sort of dispersion that's happening. And so by my just like persistence and continued effort of just applying force, the sheer force, sliding force, continually, not yet, not yet, but eventually the pigment is going to yield to that. And yeah, I've had students who just like keep adding water because they're like, oh, where did it go? And it's all just like in a big skim underneath it. And then they have like a whole soup of pigment that won't mix with the water. So going slow is really helpful. I'm about to hit a turning point here where it actually starts to mix together. Yeah, okay. So here we go. Sheer force, just over and over and over, relentless, consistent. At the beginning, I was trying to keep my knife pretty low so that it wasn't just like flying all of this up into the air at me. And now it's together, finally. So just in review, we've got this synthetic iron oxide, dense, holds its peaks. It's pretty short. Short meaning I poke it and it just stays where it is. Now this ultramarine blue that has more nodular particle shapes, more irregular particle shapes, this is longer. It has some of these rheological qualities that when I'm moving it, it's stretching out and getting all stringy and long. So that's kind of what we're seeing there. And then this is like straight up frosting, which is still like, it'll work. Right now they're just in water, but if I were to mix this with a water-based binder, all of these would make paint. but the feeling of it is going to be different. And the reason why making your own paint really sort of shows you that is because in the ready-made paints that we purchase from the store, manufacturers are using aluminum stearate, magnesium stearate, different types of materials like that, that essentially help this process. They help the pigments and the binders just mix together very easily without a lot of labor. And it also delivers a much more consistent product, which is ideal for them and ideal for some artists. You know, some artists are like, I want to squeeze out the paint from my tube and I want it to be what I want it to be. And I'm kind of like, I want to squeeze out the paint in my tube and have it be what the pigment wants it to be or what the binder wants it to be. You know, I think there's some artists that that are interested in some of these unique properties that you can have working with the materials directly and on your own. And maybe we ought to be making our own paint. So anyway, this is just about wetting pigments. The next step is to mix them with a binder, which is what we're talking about now. This is kind of like the last chapter of the talk where we're really going to go medium by medium. I'm not going to be too granular about all of the last details with this because the reality is, you know, it would just be a little too surface level to kind of cover all of these in a meaningful way, I think. But we are going to go a little bit one by one. So don't feel like you need to write all this down in this moment. We are going to kind of go step by step. And I'm going to talk really from my perspective as an artist working with these materials, using these materials to kind of give you a sense of the feel. Because all of this stuff, just like this information, these are things you could kind of compile, you know, Google and whatnot. So a few things. Making a painting, I should say, starts from the bottom. So if pigments are the melody, they're the musical notes, binders are the dynamics, there's the tempo, the rhythm, all of these things. In order to do any of those things, we have to, you know, okay, so let's pick a binder. Let's say we're gonna use distemper. We're gonna use distemper as a paint. That's gonna be my musical composition is going to be in distemper. But then the question is like, okay, so what do I paint distemper on? What kind of substrate or support is going to be suitable for distemper? Is it brittle? Is it flexible? What are its qualities? How am I intending to paint it? Because how you intend to paint something may also weigh into what sort of support you might want to use. And then from the support, it's like, okay, you probably have to prepare the support in some way. Some paints you definitely have to, some you don't necessarily have to. And so we're already starting to see how there's just like this huge array of factors that go into making these types of decisions. But you are really building like the painting, it's like you're building a matrix. All of these layers have to somewhat agree in order to function. And so if we're starting, okay, I'm gonna make a distemper painting, you have to go like 3 steps below and figure out, okay, so what does that go on? What do I put on that? What do I put on that? And then we're going to make the paint and deal with the binder and the pigment and all of those things. So it really is a whole network of decisions and factors that are kind of working together. And I think that is a theme of this presentation as well. And maybe just of life, but we don't need to go into that right now. I do just want to specify the health and safety on the bottom. I am just specifically saying additional hazards that may pertain to these mediums. It should, the sort of thing that I'm assuming here is that the sort of pigment handling practices, don't eat or drink while you're handling pigments, wash your hands, don't touch your face, wear gloves, wear a respirator, all these different types of things. Those are a part of working with pigments in general. The health and safety that's listed here are specific to mediums that I'm talking about. So we're going to go a little bit one by one, but again, not going to go too far into the granular. Watercolor and gouache, the binder is gum arabic. I showed that in an earlier slide. You saw those little resin clumps, and then the liquid gum arabic. It's a binder that by itself doesn't work that well and requires other things added into it, like honey and glycerin, perhaps oxgall, things that like humectants to keep moisture in the paint, plasticizers to add flexibility. Oxgall is a wetting agent. It kind of needs these other ingredients in order to make the watercolor vehicle. Um, all of the images that I selected for these pieces are ones that I found, have either seen or found on in the collection at the Art Institute of Chicago, because I lived there for a decade and I feel like the museum that the paintings there are mine. So that's how I selected the artworks in this presentation. Watercolor is hygroscopic, meaning if you make a painting and then 20 years from now you spill water on it, that painting is going away. So that's an important thing to consider, which is why I always recommend to display and keep watercolor behind glass. It has a very low viscosity to it. And the binder, as opposed to in those diagrams that we saw where the binder molecules were really wrapping it all the way around the pigment particles, gum arabic kind of functions just by like gluing the pigment particles together. And so in that way, it remains quite delicate. These are two works of mine where you can kind of see how I'm using watercolor. You can see in some passages it's building up and becoming more opaque with more layers of paint. You can see the edges of the different paint markings, how in this one I was using a mixture of different blues together actually, but the paint kind of goes to the very edges of the shapes. And so some of those different movements and patterns of drying are going to be different from, one pigment to the next and whatnot. But another important thing, watercolor is pretty transparent to translucent. Gouache is the same basic binder, but has whiting added into it. So calcium carbonate, barium sulfate, maybe white pigment, other types of things like that, that lend the opacity to the paint system. Egg tempera, which is like my favorite. Okay, I don't have one favorite. Egg tempera is one of my favorites. There's many different types. You can use just the yolk of the egg and just dilute it with the yolk a bit with water. You can use the whole egg where you would like pierce a hole in the top of the eggshell, shake it up and use it like that. You can mix either just the egg yolk or the whole egg with different types of oils, gums, or resins to make an egg oil emulsion paint. So there's a lot of, and that kind of paint is going to have a higher viscosity. It's a little stickier. I would say it's a stickier paint than just egg tempera by itself. But egg tempera is really like all the medieval paintings, all the icon paintings. They're all made with egg tempera because it's just this like glowing, luminous, incredible paint. The ground is traditionally like very bright white because of the transparency of the paint. You're really kind of saving your whites by the ground glowing through these translucent layers. So it does have like a very jewel-like effect to it. The paint is very brittle, and so is the traditional sort of gesso ground that's made from gypsum and rabbit skin glue. So it definitely needs a rigid support for this. These Giovanni de Paolo paintings are like some of my favorite pieces in the world. And then these are some works of mine in egg tempera. You can see some of the things that I'm doing here. I'm like carving back into it. Like these areas are kind of scratched back out. Some of these little roots are scratched back out. There's areas like these little rocks where I'm lifting back out of it before the paint has fully cured. And so it's just like an incredibly versatile and very luminous medium to work with. Casein is a funny paint. It's made from the casein protein in milk, is one of the main proteins in milk. And so it, in order to make casein, which I'll show a little bit on the next slide, I don't actually paint with casein myself. It really lends itself to a sort of like flat application. It's got a mateness, it's got more opacity. And so those are some qualities that are great for people who are trying to do more graphic things or flatter things, it's often talked about more as a coating than it is as a paint, which is not to say, I mean, I've seen some incredible casein paintings as well. This is a Sherry Levine painting. And then here we've got two videos. So basically casein, the protein itself is not soluble. And so you need to use an alkali in order to make it dissolve and in order to use it as an adhesive, as a binder for paint. So over on the left, this little video, I'll play it again. What we're looking at is we're just looking at like casein powder that I'm soaking in water. And you can see that it's like totally doing its own thing. It's not dissolved by any means. And then this little video on the right, I've added an alkali. I used borax and hot water to the casein powder that was soaking. And now it's this like delightful, syrupy consistency that is a very, very, very strong glue. This is also, like egg tempera, is a very brittle paint system. So requires a rigid support. Okay. Next, distemper. Distemper is the binder for distemper is generally rabbit skin glue or any other type of like protein colloid glue. Think like gelatin, like it's warm, it's liquid when it's warm, but when it's cold, it's a solid. It's like a gelatinous sort of solid. And so it makes it interesting to work with as a paint because it's a solid. It's a jello if you're trying to use it at room temperature. So you need a warm palette, not a hot palette. Like you, it shouldn't be above like 140 degrees Fahrenheit. Otherwise, the proteins start to break down really. But you do need like a sort of like warm water bath in order to keep the paints fluid. It also, in thin applications, works on all sorts of stuff. In thick applications, can become very brittle, which is why this Vuillard painting, which is also one of my favorite paintings in the universe, is like this thick, pasty distemper painting on canvas. And I mean, bless the conservators who take care of this thing, because I think if you stand in front of it, you can just like have little pieces falling down or something, like the trees dropping leaves or something. But so this is an incredible painting in distemper, and Vuillard used a lot of like chalk mixed into it to really kind of build up the cakey and almost pastel tones to it. But if you paint it more thinly without this sort of buildup, it does stay quite flexible because hide glue is like the used as a size painted directly onto canvases and stuff. So here's a little video just so you can kind of see what the process is to make rabbit skin glue. This ratio, I'm doing like what, six tablespoons 15 milliliters, is that right? Into a quart of water. And so I'm mixing, I have just cold water that I'm first just kind of hydrating the glue, stirring it in. You can read the package, different packages are gonna have different instructions. I kind of do them slightly different anyway. But first you just kind of mix it together is what I like to do. And then I'm putting this on a double boiler. There's water in the bottom pot. Warm it up on the top. It's kind of like a watery applesauce consistency. There's like a graininess to it. And you can notice that I can't see the bottom of the pot right now. I'm gonna stir it. I did check on it throughout. Like I don't just leave it because I don't want it to get too hot. Again, you should always be able to touch your glue without burning your finger or something. And now it's ready, and it's translucent because all of the little granules of rabbit skin glue have melted into the water. We can see through it to the bottom of the pot. And then you kind of can test the adhesion. Put on your fingers, let it dry, stick them together. You can see it has some pretty good adhesive qualities there. So that's what that looks like. Acrylic kind of similar, not similar. You know what, before I talk about acrylic, I just want to mention that all of the binders that I've said until this point have been natural binders. And all of them are binders and materials that have been used as adhesives literally since like ancient times. Yeah, both as like binders for pigments and just as like glues for other sorts of things. So talking casein, water-soluble tree resins like gum arabic, egg yolk, hide glue, things like that. And now acrylic, not so much, right? Acrylic, it's an acrylic polymer emulsion. We're talking about uh, resin. It's a plastic essentially. And so the acrylic polymer, the acrylic resin itself is not actually water soluble, but it's like polymers of acrylic that are suspended in water. And the water has like a bunch of other stuff in it too, other chemicals like surfactants and defoaming agents and antifreeze and thickeners and pH buffers and all sorts of other things in the water too. But what happens is as the water evaporates out, um, the polymers of acrylic, the resin, kind of knits together and adheres together, which is again why it does lose um, volume. But it's extremely, extremely versatile. You can really do all sorts of different things with acrylic. And seemingly there's just like less rules to follow than other paint mediums, and it'll still probably work. Whereas a lot of other mediums is like, well, if you don't follow the rules, like your painting might crack in half. With acrylic, you do have some literal flexibility and also some process flexibility as well. There are downsides though. I mean, we're talking about waterborne plastics. And so when you have water that you're cleaning your brushes with, like this has acrylic resin that's floating in the water. And so in terms of disposing of these materials, not pouring them down the sink, things like this, they're very important environmental things to consider with acrylic. So it does have some like superhero like qualities of just you could do anything, but then it's like that a price, and it's our responsibility as artists are with our own materials, not um here's an acrylic painting that I did. And you can really see like the different types of textures that are all able to just sit side by side here. This is like I scraped into this, and in some places it's like very matte, and in other places it's extremely shiny. And then there's other, this white is like built up on top of the shiny part. And so this is kind of what I mean about the versatility of being able to use these like wild textures and wild surfaces and do some funky things with them. Next up is oil, the most luscious of all the paints, perhaps. This is a Van Gogh painting, of course. The binder for oil paint is usually linseed oil or other drying vegetable oils. Linseed oil is the best. I mean, it stays the strongest and most flexible over time compared to other drying oils. It dries through oxidation. So all the ones we were talking about were, evaporation and whatnot. Oxidation, it's again, the oxygen is going into the paint film, and there's like a thermal kind of process that happens in the oxidation process. It has a permanent cure, higher viscosity, long working time. It does become brittle with age. It also becomes more transparent with age. So even though at the beginning it's nice and flexible and is great on canvas, over time, a rigid support really becomes pretty crucial for a lot of oil paintings. There's also working with oil, because it is a thermal process of curing, the oxidation process, like you have to be really careful with disposal of oily rags and things like that, because what happens is if there's paint that is bunched into a rag that's just crumpled up or something, there's this like thermal reaction that's trying to happen. And when it's trapped inside of a rag, they can spontaneously combust. And so there are a lot of ways to avoid that, like having red fireproof cans to throw your rags into, to always leave your rags spread out and never crumpled up, to soak them in water, and then take them to a waste disposal place. There's many different ways around this. But I also just want to say one huge misconception about oil painting is everyone says, oh, it's so dangerous, right? Like it smells. It smells. And it's like the solvent that we use to clean our brushes emits VOCs, and those can be hazardous to breathe, definitely. But like the oil paint by itself doesn't have solvent in it. And so those are not emitting, it smells like oil, but it doesn't have harmful materials that we're inhaling, actually. So if you omit solvent from your oil painting practice, you're actually not breathing in anything dangerous. You do have to be careful with the combustibility of rags and stuff like that. But in terms of respiratory issues, um, oil paint by itself is not a hazard for these sorts of things. It's any solvent or mediums containing solvent, which is a lot. Um, but yeah, just so you guys are aware of that. And I mean, there's just a reason why oil paint is one of the most prevalently used mediums. It's just like so luscious and so jewel-like while still being able to like build up a sort of texture and thickness to it in ways that a lot of other mediums don't quite allow for. So um, I think in this painting, in this detail, you can really see some of that like thin to thick, the texture and the transparency and all of these things that can kind of happen in the world of oil. Finally, our last medium, we're talking about encaustic. The binder for encaustic is beeswax. Usually it has a hardener in it, such as damar resin. I would always use carnauba wax instead. The drying mechanism is just like solidification. So when we paint with encaustic, we're using the wax when it's hot. So it's a very bizarre process. Like all in every other type of paint, you like take your brush and you put the paint and you can make this beautiful stroke. With encaustic, by the time you get your brush over to the surface, the paint is solidified, right? And you can't move it. So you're really reliant on heat guns or other sorts of like heating implements in order to bring that expression into your painting while you're working on it. Um, Absolutely bizarre, amazing paint to work with. This is an Arthur Dove painting. Again, it's on encaustic on canvas. It's, I mean, we all know how wax moves, like it's not very flexible. So um, definitely should be on a rigid support. A lot aren't, like all the Jasper Johns paintings, encaustic paintings, like those are on canvas, Um, Health and safety, we're using hot materials, gloves to avoid burns, huge fume hazard if the wax is heated above 200 degrees Fahrenheit. The actual flash point of the wax is like above 400 degrees Fahrenheit, but I've seen some things happen. So definitely encaustic is not for the faint of heart. Definitely a lot of research necessary. Um, and the other kind of beautiful, crazy thing about encaustic is that if you finish a painting, kind of like watercolor, finish a painting 20 years ago, if you take a heat gun to this, it would all just melt off. It would just be gone. You could just blow the whole painting right out of there. So this is a encaustic piece that I did. You can see some really melty areas. You can see some more built up areas, a lot of areas that I carved back into, and even carved back down into the wooden substrate for this. So the working qualities of it are basically like forget everything you've ever learned about painting because it's like not relevant here or something, but it's really, really interesting. And also encaustic is a fantastic medium if you're interested in collage because it really preserves the paper. Um, Acrylic also is a great medium for collage, but most of the others you can't really incorporate collage in a very meaningful way. But encaustic is really great for that. So that's a fun fact. We are back to pigments, people. I just want to end here, come back to pigments before we close. Because this is like really, I don't know, what it's all for. The pigments are the story, they're the song, and the binders is like how do we tell it? How do we sing it? So these are some pigments from the pigment archive I made last year in Santiago, Chile. And that's all. So thank you.
Wow, that was phenomenal. Thank you very much. That was really, really fantastic and very inspiring for sure. Yeah, I've got like tons and tons of questions.
Oh
Uh,
man.
uh, that's a question that is like I think was Tanya, no, was Cynthia like summarized very nicely. Is there a plant-based alternative to high glue?
Um, Probably. A lot of people, I don't know if it might be more, I don't know if it would act in exactly the same way, but there's definitely alternatives, right? Like you could use starch-based things, methyl cellulose-based things. Um, it is true that with like, I don't know, same thing with like leather, like vegan leather, a lot of it is like made out of plastics or things like that. So you can
Yeah.
get into some issues there. You know, like Aquazol is a synthetic binder replacement for gum arabic. But it's not a natural thing, it's a synthetic thing. So I don't know that anything comes to mind as something that's like actually um, a
Could you
suitable
use, yeah, for example,
plant-based
chitosan?
exchange. Sorry,
Could you use a chitosan? Like
I'm not familiar with that.
yeah, it's a similar to like you find like any crustaceous shells that you find there, you just crush,
Okay.
then you make a very nice kind of a paste out of that. We
Mm.
use that a lot in the lab to glue stuff.
Oh,
And
cool.
and agar as well, like mentioned here, that could be used that as an alternative. Yeah, soy milk. Yeah, yeah, that's
Yeah.
another. As long as you have a protein or a long polymer kind of structure that you kind
Yeah.
of create bind like ability, right?
Yeah. I mean, in terms of like what suitable plant-based adhesives, so many. In terms of a plant-based adhesive that would behave the way rabbit skin glue behaves, that's the part that I'm not so sure about. Um,
Yeah, so that is another. In the meantime, I tried to sort it out, the questions here. Feel free to mute yourself and ask the question. That's totally fine as well.
okay.
So I'm just trying to sort it out before we ask the next question here.
To ask a question as a follow-up to the rabbit skin glue. I was actually more interested in an alternative to preparing the surface structure. So I recognize in this case it was presented as a binding agent, but in terms of like creating a gesso base, for example, um, what could be used in place of the rabbit skin glue? The methyl cellulose.
Um, I think methyl cellulose works well as a replacement for gum arabic. Um, I don't know, even building up gesso, it's like so many layers at any um to really get that same kind of surface. I think you would need to do a lot of experimentation to see what might work. But from my experience with some other plant-based binders, I don't know what would truly emulate those types of qualities. But yeah, please keep me posted if you do dig into exploring that.
Yeah, for pescatarian fish glue, that's very nice. So, do you have a book that explains all of these with a clarity that you do, like in a very well detailed and do you have any book to suggest us
Yeah,
look?
I've got a bunch of books. To be honest, I don't have like just one book that is like, okay, this is the book for everything. But I find like I go between different handbooks in order to get different kind of sides of the story. Like Ralph Mayer, his handbook on materials and techniques, is just old and kind of dated at this point, but does have a very sort of in-depth analysis about why a lot of things happen. So his handbook is good. Mark Gottsagen has one that was published. Oh man, hmm. I'm not sure how long ago. I would say less than 20 years ago. And that one's a really good reference for just like if you're looking for fast facts and recipes, you're not looking for all this fussy behind the scenes stuff. You're just trying to get it done. That's the book. That's the best book, in my opinion, for just like, give me the facts down and dirty. I'm trying to make this today. Don't
Sorry,
really
can you
need
repeat
all
the name of the book?
um, the book is called like the Painter's Handbook. I don't know what it's called, but it's like the handbook. They're all kind of called like the Handbook of Materials and Techniques of Painting or something. But the author is Mark Gottsagen.
Thank you.
I'll put it in the chat.
Yeah, that would be very helpful, actually.
Something about like that. Ralph Mayer, Welty. I forget his first name. It's like Kurt or Carl. He's a German guy that did a lot of research on casein. A lot of these books, as they were published, it's like I mean, and also all of these go back to Giannino Cennini. I think I probably put an extra N in there somewhere. But the sort of like original medieval manual on materials and techniques that you can kind of trace it back. Like a lot of the in the United States, the kind of revival of classic materials and egg tempera with Isabel Bishop and Andrew Wyeth that kind of followed the Giannino Cennini text being, oh yeah, okay, Lawrence has the Gottsagen book. If you guys can see his screen. I know there's a lot of people on here. Revised and Expanded, the Painter's Handbook, it's called. Yeah, that's the Mark Gottsagen title. So anyway, that's a quick sort of
Yeah, I've got a couple of
version.
books as well that I could share with you all later.
If any more specific, like I'm seeing things like if there are any more specific book recommendations, those are kind of like general overview ones. And like I said, I do pretty like I bounce between them. I don't listen to any one over another. And you also have to know that it's like as there's more research being done in conservation realms, as things are further contextualized, conservation, archaeologists, chemists, people like this, they're the ones that are discovering a lot of the newer advances in what's happening. Following technical articles from paint manufacturers, like Golden has a newsletter, Just Paint, which is fantastic, and Natural Pigments has a lot of technical articles on their website that are extremely useful. I'll type those in the chat too.
All right, so let's see, there's another one here. To your knowledge, does the shape of pigment particles impact preservation? Or it's more really on organic versus inorganic components? This person is very curious. If the more densely packed, uniform shapes tend to stick more.
What was that last part? If they're more packed
So the
uniform
person
shapes,
tends to
stick more.
like
I found it.
that's packed more than all the uniform shapes.
Yeah. Okay. Shape of pigment particles impact preservation. I don't know that it would impact preservation so much. Yeah, I would say to my knowledge, I don't know whether it impacts preservation in terms of, I take that to mean like how conservators would preserve a painting. But maybe also the question means whether different particle shapes would impact the longevity of the painting's life, in which case I think the answer is yes. Because I think if it's more regular particle shapes, it can crack more easily. Whereas if it does have more irregular particle shapes, they can kind of knit together on a mechanical level, like I was kind of describing with the paper, the different types of paper, imagining ripping them in half. I think the same logic would apply to paint films. So if that's what that question means, then I think it would impact. Sorry?
Yeah, sorry, that was the question I was asking. Thank you.
Okay, good. So I answered it for you. Good.
All right. So is there other ways to verify how different forms of linseed oil will impact in producing like paints afterwards. So if you use different sources, it would be the same, or it doesn't have any impact on the end result.
Different types of linseed oil.
Yeah.
Yeah. So it would have a very big impact. I mean, I almost included slides about like the refining of linseed oil, but then I was like, no, that's too much for this amount of time. But no, so depending on how an oil is prepared, and again, this is something that's like all done. Like this isn't even something that like paint manufacturers do. This is something that like linseed oil manufacturers do. Like this is it's kind of, but it's basically like pressing the seeds. There's a hot press or a cold press method. And there's different reasons to use different oils. There's sort of like the alkali refined. It basically has a lot of the acids and things that are stripped out of it, and then other types of things that are added back into it that should have stayed in but got stripped out in the process of making the oil. So if you're just trying to like bootleg it in your bathtub or something, I think that would probably be a bad idea for making a good linseed oil for oil paint, because you're going to have acids and all sorts of materials that are going to be a part of it that are going to negatively impact the paint. But I think in terms of a lot of there are definitely methods for refining it in your own studio. So not to say you can't, but if you're trying to like press, I think most of the people that I know who have done that, they're starting with they're like not starting with like flax seeds. I don't um I don't know exactly what they're starting with, but they're not starting with like flax seeds and pressing it themselves. But the point is, there are, yeah, a lot of different factors that, in terms of acidity and other components within the oil, that could have a big negative impact to the paint, and different types that would have different results in using them with paint. So.
Okay. And what would be more flexible binder? Traditional / natural, the distemper in thin layers? So I think it's two questions in one, but yeah.
Mhm. Well, I think that most of the traditional binders are actually much more brittle. Um, Probably acrylic would be the most flexible. Oil might be the second most flexible. Distemper, this is also loose and depends on how you use it. So don't like, quote me exactly on this. Distemper might be the most flexible of the more traditional natural binders if used in thin applications, is what I would say.
When we say like flexible, we are talking about the rheology properties of the binders, right?
So when
Or
I
not?
say flexible, what I'm talking about is like when it dries, is it
Oh,
going to be a
gotcha.
brittle material or a flexible
All right.
material?
Okay.
Yeah, is what I mean when I say that. So like egg tempera, when I say it's very brittle, the binder when you're painting with it is quite fluid, but then when it dries, if you had it painted on canvas, for example, it would crack completely. Yeah, in terms of flexibility, I'm talking about like the dried paint film and what sort of support is going to be rigid enough for that paint.
So, and what will that cause like at the molecular level, right? That's a very interesting thing to look at as well. Kind
Yeah.
of at the very tiny, what would happen like at that specifically interface binder like the paint and the medium that
Yeah.
will to give this flexibility. Yeah. That's another question. Okay,
That's
so
a question for you.
need to answer, right? Yeah, that's I'm gonna pose those questions next week in my group meeting. Okay. Any more questions? I don't know if I don't see this here in the chat. Does anybody wants to unmute and speak freely?
Yeah, I got a question.
Yeah.
You were talking about the refractive index and the shape of pigments. What would be of most influence for the tinting strength of different pigments? Is that of like any of those factors, or?
That's a good question. That's a really good question. I think it's a combination. I don't know that tinting strength. And so just so everybody knows, tinting strength is often like, how pigment or paint makers will label, like if it has a high tinting strength, it means that it's like very strong and overpowering when you mix it with other colors. If it has a low tinting strength, it means it's what is more likely to be overpowered by the other colors. I do think that the tinting strength is probably a whole array of factors that would include refractive index, that would include the particle size, and that would likely just like include the chemical composition of the pigment as well. Yeah, as I'm thinking through it, I think that I think the factors there are likely quite intertwined in terms of determining what is, the thing directly determining the tinting strength.
I've been thinking about it, and I've been looking at, you were talking about refractive index, and I've been looking while you were talking as well. But like there are so many different pigments that are very fine or very small particles that either one has a very high tinting strength and the other one has a very low one. So I really don't see any kind of line in it or any resemblance.
Yeah, I do think that is likely drawing more on just like the chemistry of the pigment and less about the mechanical sort of physical qualities of it.
Yeah.
Yeah, because you're right, like it's not a systematic thing.
No, unfortunately not. No. Thanks.
Yeah, I hope that helps. Judith, do you want to go ahead?
Yeah. So I can definitely answer the questions as far as the flexibility. I've been researching Japanese painting for over 20 years, and they roll, as you know, the paper with the pigments and their natural pigments, ranging from very fine to very coarse. And so they're using a seaweed glue, and various hide glues. And the hide glues are not rabbit skin glue because that will crack. So it's basically, there's different deer glue and cow glues and all different ranges of them that are more flexible and have preservatives, etc. And for the different particle sizes. So that would be the answer. It's the most flexible glues would be the deer glues. And then there's also a seaweed glue for very, very fine particles like mica. So they have figured out the system. And it's very much, you answered the coarse particle versus the fine very accurately, that you can't keep putting fine. You need a coarse in there to latch onto it. So that they'll stay on there, but as you raise up the surface, you weaken the glue. And that's how they're getting their pigments on their screens and scrolls to last for thousands of years.
That's amazing. So, I mean,
in a short nutshell, that's just a short answer for that. But yeah.
Thank you for sharing that. Yeah, I would love to learn more about the research that you're doing. That's amazing.
You can email me about that.
There's, it's pretty amazing.
Yeah.
There's so often
out, Judith. Your email is going to get flooded now.
It's Judy at judithkruger.com. judithkruger.com. So yeah.
So often the actual knowledge of what are the different types of proteins being used as binders or something, that's, that knowledge just kind of gets lost. They're like, yeah, it's glue, so it's amazing that you guys are able to detect all of that.
And the same thing to say like seaweed. There's tons of seaweed. Like
So it's called funori,
Oh, okay.
Funori, and you'll see it on conservation sites. But really, the hide glue is the key.
Thank you.
And did you guys use any specific technique to identify those type of behavior or flexibility?
So it's a very known thing in Japan that if you go into a pigment shop, you will see a whole wall of the 50 different kinds of glues, including hide glues, and each one is for a different purpose.
Oh, wow. Okay.
That's amazing.
All right. Any more questions, comments, suggestions? All right. So I don't see any more questions here? So I would like to invite you all to thank Elisabeth again, once again, for this wonderful and informative presentation. So yeah, thank you very much, Elisabeth, and thank you very much, everyone, for attending this SUMA seminar. So stay tuned in the next email list that we're going to be sending out. We're going to have like other speakers as well, talking about binders in a various different ways, and also we're going to go like through more technical aspects of it. If there's anybody interested in that very high level, like chemistry and physics and characterization techniques. All right. So thank you very much, everyone. Have a great day, a great evening, and the recording will be available on YouTube, either Ready Institute or PRI. All right. Thank you very much.
Thank you.
Thank you.
Thank you.